Welcome, everyone. My name is Polly Fleischman. I'm the second VP of Permian Basin section of SEPM. Today, we're having Jens-Erik Lundstern, research geoscientist from the United States Geological Survey, talk to us about geomechanical considerations for understanding and managing induced seismicity. So Jens Lundstern is a research geoscientist at the USGS who studies tectonics and geomechanics focused on induced seismicity, unconventional energy, and the geologic history of the Western United States. He received his PhD in geophysics from Stanford University, where he developed a new generation map of the state of stress in North America. Dr. Lundstern he received his master's in geological and environmental sciences also from Stanford, where he studied the tectonic and paleogeographic history of the Great Basin in the Western United States. He has previously studied the Alpine Fault plate boundary system in New Zealand on a Fulbright Fellowship, and his experience includes work for Statoil, which is now Equinor, as an exploration geologist in the Gulf of Mexico. Everyone, please welcome Jens.
Thank you, Polly. Hi, everybody. I'm Jens Lundstern. As you may know, my name has changed recently because my wife and I had a baby and we wanted to have all the same name, and my prior name was very complicated. And so if you see Lundsny on slides, that was my maiden name. And now it's Lundstern. So you'll see both. And let me know if you can't hear me or can't see something or something doesn't make sense or whatever. I'm happy to talk about that. So I'm going to talk about a topic that I think is on most people's minds here, which is injection-induced seismicity, focusing on West Texas. Obviously there's been an increase in seismicity here, and I'll talk about mechanisms for how that can happen. I'll talk about the critically stressed crust, which is a very important sort of fundamental understanding for that. And we have lessons from places like Oklahoma that can be applied here to hopefully get the seismicity rates down. And I'll talk about, in particular, work that I've done with Mark Zoback, mapping the state of stress across North America, focusing on the Permian Basin most of all. And then we'll talk about seismicity here. So you all have seen the headlines, I'm sure, that there's been an increase in seismicity here. The press, the national press, is I think started paying a lot more attention after the November event, and I think this headline over here by Forbes I think is really nicely evocative. In West Texas, water is scarce for fracking, expensive for recycling, cheap for disposal wells, and it causes magnitude 5 earthquakes. So that's the narrative that the rest of the country is here. Okay, about induced earthquakes. There are a few ways that humans can trigger earthquakes, and it's been known since I think the early 1970s, if I remember right. Usually it relates to changes in the pore pressure in the subsurface. That can be due to depletion, but much more commonly, especially in this part of the world, it's due to pressure increases associated with some form of fluid injection. And so most of the time, as we'll discuss, the injection-induced earthquakes are related to produced water disposal. And I'm showing sort of two different depth ranges where that can happen for reasons that will become apparent. And normally that's fine, not a big problem. But if there is pressure communication between the injection interval and faults that are well-oriented within the stress field to fail, then you can trigger earthquakes on those faults. And the mechanism for that, as many know, is increasing the pore pressure will result in a decrease in the effective normal stress that's clamping that fault shut. Those are those inward arrows there. And if it's a well-oriented fault in the stress field, that means that there's already shear stress naturally built up on that fault. And so it is, that shear stress can be relieved in an earthquake. Usually these are faults that would have failed at some point anyway, but are being made to fail now. It's also possible to trigger earthquakes during hydraulic fracturing operations, very high pore pressures in the area of the wellbore. If there is a fault that crosses the well pad or is very close by, within the narrow zone where the pore pressures are very high, you can trigger earthquakes. Also, because the pore pressures are so high, it's not necessarily the best oriented faults. It's more orientations of faults that can fail, and of course, by definition, hydraulic fracturing is triggering just tiny earthquakes in large numbers. So that's the sort of fundamental types of causal factors that we're talking about. And remarkably, most of these earthquakes, particularly when we're talking about saltwater disposal related earthquakes, are associated with very small pore pressure increases, usually spread over a very large region. We've seen this very kind of remarkably in Oklahoma and Kansas. That's what's shown here. These are all pore pressure models for different areas: Oklahoma, Kansas, Fort Worth Basin in the center, and the Delaware Basin, a recent pore pressure model on the right. And all of these, we are talking basically pore pressures of usually around 200 psi or less. So usually less than about a megapascal. And this one on the left here shows especially low values. There's some question about that, but regardless, we are seeing, in the case of Oklahoma, thousands of magnitude 3+ earthquakes in a few years related to billions of barrels of wastewater disposal, for the most part, spread over a large region, causing very small increases in pore pressure. When we drill down on specific cases, you can see this in more sort of mechanical detail. This is work that I did with Mark Zoe back in 2016 when we published our first stress map for Texas. We looked. This is the Azle set of earthquakes here, just west of Fort Worth, and that caused a stir in the press when it happened. And there was very little stress data at the time. So when we looked at the state of stress there, we found that the faults that failed, represented by these nodal planes on these focal mechanisms that were previously published, were basically perfectly oriented for failure and would have required a very small pore pressure increase. And we see something like that in most cases where we look at these, more or less. So why is it that such small increases in pore pressure can result in a wide range of earthquakes, from tiny to potentially damaging? It's because, in general, it appears that the crust is critically stressed almost everywhere. The brittle crust is critically stressed due to the replenishment of tectonic stress accumulating, and the best oriented faults continuously failing and relieving that stress. And so what that means is that deep borehole measurements have shown this most clearly, that if you measure the absolute stress magnitudes, so that's what's shown here, this is the ratio of the maximum principal stress S1 and the minimum principal stress S3, you get exactly the ratio you would expect, the values you would expect of differential stresses if the crust was, if the strength of the crust was limited by the most well-oriented faults, and specifically with a frictional strength, a frictional coefficient of about 0.6, maybe up to 1, but very commonly 0.6. And this has been shown in other ways. On the right, the red dots represent cases where it's thought that impoundment of reservoirs on the surface has triggered earthquakes. The black dots are the rest of the earthquakes in those areas of those magnitudes. And in many cases, it appears that reservoir impoundment, which is a very small increase of stress and maybe a little bit of pore pressure near the surface relative to the stresses already stored in the crust, can trigger, in some cases, very large earthquakes, up to magnitude 7+ in parts of Asia that are otherwise stable, like the Indian Shield and Eastern China here, and quite a few people have been killed by some of these earthquakes. So it's just another indication of the likelihood that we're dealing with critically stressed conditions, even where the strain rates are low. Oops. Okay. So Oklahoma provides us some useful, hopefully, lessons. There's some analogies to be drawn here. And it's also another indication of how small changes in pore pressure, as I mentioned, can result in substantial seismicity. And so there's been a lot of work done on Oklahoma over recent years. What I'm showing here is the rate of seismicity increase since 2000, and there was a kind of a sharp increase around 2014, and now it is going down pretty quickly, largely due to a decrease in SWD in the deep intervals. But these earthquakes are mostly thought to be associated with deep disposal into the Arbuckle group, which is just above the crystalline basement, and that pressure migrates down through the more permeable faults, which also tend to be the ones that are close to critically stressed, and can trigger seismicity. So one thing that Oklahoma enables us to do, because of the thousands of magnitude 3+ earthquakes that have occurred there, is we get a view of what the basement fault networks look like when they get lit up by a pore pressure increase. And I'm showing here a new earthquake catalog by Park and others for this. So this is the Kansas-Oklahoma line here. These dots are all earthquakes colored by depth. So red are deeper ones, down to 8 kilometers or more, and then up in the kind of pink purple range, and white are shallower ones. These are all, you can see they're pretty deep, mostly 4 kilometers or more, down in the crystalline rocks. But what they've done is they've improved on prior catalogs. They used a deep learning method to detect the earthquakes, pick the phase arrivals, do the locations. This resulted in finding 300,000 plus events of, down to much lower completeness magnitudes than were previously available. And they relocated these with a double differencing technique, which, as I'll show, allows you to see planes form in some cases with really great fidelity. So I was playing around with this data set a while back, and I just went through and manually identified about 1,500 clusters of events that form nice lineaments, seem to be making planes in 3 dimensions. This is the northern half of that of the catalog here. So this is the Oklahoma-Kansas line here, if you can see that. And the red lines represent faults, planes that were fit to those manually interpreted groups of events with eigen decomposition. And I'm showing a video here. This is a blow up of this area with these nice en-echelon faults. And you can see in cross-section view, they're steeply dipping. They're also very nicely constrained in many cases. These events really form some quite interesting planes, and some of them are close to vertical and some are closer to 60 degrees dip, let's say. But you see that there's a wide range of scales of faults that are being activated, and clearly there are sets of them that in some cases seem to be well-oriented and are all failing together in these networks. So we can take those planes, and again, this is just the northern half of the catalog here. So let's see if I don't know where my mouse went. Oh, there it is. So it's this northern group here. Since we know the state of stress in the area, we can compare the orientations of faults to what's known about the state of stress. This is a map of the Oklahoma, southern Kansas area from a recent paper by Mark Zoback and me in AAPG Bulletin. The black lines represent measurements of the maximum horizontal principal stress orientation, mostly from borehole measurements. And the color represents the style of faulting. So in this area, we have mostly strike slip faulting. That's the sort of green color with some normal faulting. SHmax is, about north 85 east or so close to east-west. And as you would expect, the planes are striking about 30 degrees in either direction of SHmax, which is what you would expect for strike slip faulting if the Coulomb criterion applies with coefficients of friction of around 0.6. Planes dip very steeply, so consistent with normal faulting, but we also see planes that are subparallel to SHmax and dip a little more shallowly, which would be consistent with normal faulting, and the focal mechanisms here support that. So one of the bottom lines here is that we have the information we need to avoid injecting into potentially active faults. Oklahoma is a tricky case because, as I mentioned, the fluid pressure is migrating outward, so it's hard to limit the locations. But that's also it's hard to limit where the pore pressure goes. But that's also instructive about the types of places where you might be more careful about, say, wastewater disposal. And I'll say, can be avoided if we understand the subsurface well, and that includes not just knowing the state of stress, but also knowing faults, which is usually one of the hardest things to know, especially in the crystalline basement, rock properties like permeability, and the pore pressure change that you're dealing with. So, which brings me to talking about the state of stress that we've mapped. This is now something that in many places we know pretty well, and this is why it matters more in a little more mechanical detail. This is a Moore diagram, which, for those who don't know or intentionally forgot what these are, it's just a plot of shear stress relative to normal stress for a plane, fault plane of any orientation within a known stress field, and that's what's shown here. So these the Moore circles represent a stress field where SHmax, the maximum horizontal principal stress, is greater than the vertical principal stress and much greater than the minimum horizontal stress. And so each of these dots is a randomly oriented plane in this case. And because the crust is critically stressed, that means that there's a narrow range of orientations of faults that are well oriented in an area, and they're probably failing over and over again in Earth's history, whether that's every few hundred years or every few 100,000 years in more stable parts of the world. And so that's represented by this red dot here, which are the well-oriented faults. So anything that touches the Moore Coulomb failure line, shown here for, as I mentioned, a coefficient of friction of 0.6, usually works well, is considered critically stressed, and so that might become active. But as will be important later, we don't know for sure that fault is going to fail or when it touches the failure line. We still can't predict earthquakes, and we may never be able to predict earthquakes. But what we do know is that fault is probably within one earthquake cycle of failing. So it is one of the faults that you would expect to be active as it touches the failure line. If you increase the pore pressure, most people are used to seeing this as the Moore circle moving to the left, which is if the x-axis here was the effective normal stress, I'm showing just plain normal stress. So it's the same thing as the failure envelope moving to the right. So that increases the range of orientations of planes that can become active in that stress field. And if you keep doing it, let's say, a fault fails, you might have an orientation for that fault based on a focal mechanism or, aligned groups of events like we were talking about for Oklahoma earlier. So its orientation. If you know the state of stress, you can estimate the amount of pore pressure that would have been required, at least to bring it to the failure line. So that's useful. And okay, and so how do we measure the state of stress? Well, it's actually, we have some advantages because of the nature of the Earth. Having a free surface with a free interface with a fluid, air, means that no shear tractions can be resolved on the Earth's surface, and that results in usually the three principal stresses, which are mutually perpendicular, one of them being close to vertical and the other two being close to horizontal in most cases. So that simplifies things greatly, and that means to understand the orientation of the principal stresses or of the stress tensor, you just need to know the orientation of one of the two horizontal stresses, usually by convention that's SHmax, maximum horizontal stress. And the only other thing we need to know for most of our purposes is the relative magnitudes of the three principal stresses. So we don't even need to know the absolute magnitudes of the principal stresses. And that's what's shown here. This is the classic Andersonian faulting that most people know, where you have normal faulting, extensional faulting when the vertical stress is the greatest, strike slip faulting when vertical stress is intermediate, and then compressive state of stress, reverse faulting when the vertical stress is the least principal stress. And then SHmax orientation tells you which strikes of faults are going to be the most sensitive. And so we are fortunate to have received a large amount of data from a number of companies, and sort of the gold standard type of data, as I'm sure you all are aware, is the use of borehole image logs, especially in subvertical boreholes. So this is a view of an unwrapped view of a borehole image log for a subvertical well, and these fine lines are drilling-induced tensile fractures, which form parallel to SHmax, and the dark zones here are borehole breakouts, which form perpendicular to SHmax. You could have one or either or neither of these in a given well or a given interval. If you have enough of these, they can tell you something very useful about the SHmax orientation. Similarly, now that we have good microseismic monitoring for hydraulic fracturing, because those hydraulic fractures propagate in the direction of maximum horizontal stress, the cloud of seismicity around them, this is a map view of the center well being stimulated, colored by stage. So we know we can see the hydraulic fracture propagating based on the cloud of events around it and get its orientation, and that can provide a very nice orientation of SHmax in many cases too. Earthquake focal mechanisms, or beach balls, are useful as well. Unfortunately, individual mechanisms are not good enough to give you a reliable SHmax orientation. But if you have, let's say, 30 of them or more, you can do an inversion, and obtain an SHmax orientation and relative stress magnitudes, in some cases with very good precision and accuracy. And with individual mechanisms, although you can't get an SHmax orientation nicely, it does tell you something useful about the style of faulting. Are we in an area where there's normal faulting or strike slip faulting, or as I'll discuss in a minute, both happening in the same place? And so that's how we've approached mapping the relative stress magnitudes. We've done stress inversions where there's enough mechanisms in a localized area, and we have done we've interpreted the style of faulting based on individual mechanisms or groups of mechanisms, applying the appropriate uncertainties to those in the rest of the continent. And so this is the result of that. I won't talk too much about this because I know some of you have seen this. So this is our new map of North America, the state of stress in North America that we published 3 years ago, I guess. And the black lines again are SHmax orientation. So many of those are boreholes. You can think of that as a point measurement in that location, and that's the orientation of maximum compression, horizontal compression you would feel if you were in a borehole at that depth. And the length of the line corresponds to data quality, so longer lines are higher quality data, and we're not showing data that we consider unreliable. And then the background is the style of faulting interpolated in this way, and we're using what's called the AFI parameter by Bob Simpson, which is a very simple way to depict the relative magnitudes of 3 numbers. And it's a continuously varying number that goes from 0 to 3, 0 being most extensional. So that's the very rare case of radial extension here in dark blue that we don't see very often. 3 is the most compressive possible case, which is, sorry, I keep doing that, which is radial compression. Again, that's not something we see very often, but what we do see is everything in between. And so this can capture everything from the Andersonian states of stress I showed you, where normal faulting is 0.5, strike slip faulting is 1.5, and reverse faulting is 2.5 in the very pure Andersonian cases. But there's also transitional states that say range between 0.5 and 1.5, where you can have both normal and strike slip faulting happening in the same place. It doesn't mean that the stress field is very complex there. It probably just means that the vertical stress and maximum horizontal stress are similar in magnitude and greater than the minimum stress. And importantly, you'll see that most of Texas is this sort of teal, light blue, and approaching green color. So this is very relevant for this part of the world. We deal with more extensional states of stress where both normal and strike slip faults can be active. Further east, you see that the continent becomes more and more compressive, and we have more reverse faulting on the eastern seaboard. Note also that the SHmax orientations further to the east are fairly consistently northeast-southwest, but they go through what looks like a clockwise westward rotation to be more east-west, as we saw in Oklahoma. And there's a lot of variability in parts of the western US, which looks chaotic here at this scale. But if you zoom in on those areas, we actually see a lot of coherency to these. The data in these 2 circles are all new, from contributions from companies. And when I was presenting this to an industry consortium that funded this work, somebody asked, is it possible that we're looking at rotations of the SHmax orientation with depth in these areas, not just a change laterally? So we looked into that, and lo and behold, that does not appear to be the case. We don't. So this is the Uinta Basin here in northeast Utah, and this is the Denver Basin here in northern Colorado. And I broke it out into the blue area, blue SHmax orientation population, which are more north-south in both cases, and black is more east-west in both cases. And here I'm showing their depth. And you see there's no rotation apparent with depth. And it's especially clear in the Denver Basin, where there's a lot of overlap between the depths, but not rotation happening. And this has been, argued for a long time, but it's nice to see the data so clearly. By the way, just out of interest, these orientations of SHmax, these short distance rotations that we see seem to be located just around the margins of these extensional provinces in the western US, like the Rio Grande Rift, and here's the basin and range. This is the Wasatch Front over here. I don't think anybody has explained these yet, and I am quite curious what's causing that, because that sort of behavior was not really expected before. So speaking of that sort of stress field, now to the Permian Basin, where we published a map of the state of stress in the Permian Basin in 2018. This is an update to that from last year. As you probably know, SHmax rotates in a very interesting pattern from north to south across the Delaware Basin here on the west. So that's about 150-degree clockwise southward rotation of SHmax that happens, and it's fairly smooth, although you can see in some places it seems to happen more quickly in space than in other places. Whereas if you go east over the Central Basin Platform and Midland Basin, the SHmax orientations are more consistent. There's some local variability that may be kind of localized around faults, and then it starts to rotate. I guess that would be counterclockwise eastward out of the Permian Basin. And note that the style of faulting here, as I mentioned earlier, is both normal and strike slip faulting. We think it's a little more compressive in the Midland Basin, Central Basin Platform. We think it's closer to strike slip normal there, as opposed to in the Delaware Basin, a little more normal with some strike slip faulting. The recent earthquakes that many of you here probably felt produced focal mechanisms. So they occurred on faults that look pretty well oriented within the stress field. So that's helpful to know that is indeed happening. So this is the 5.4 in the Mentone area that happened in November, and here's the December event near us here, 5.2. These are USGS numbers. Note also, an important point here is that, and I'll go back, not only, so we have these rotations in SHmax orientation that look quite coherent because we have so much data, and it's really good data, but also note that the different measurement techniques are all agreeing with each other. So the outward pointed arrows represent aligned microseismic events. The unadorned lines are from boreholes and so on. And if you look at the focal mechanisms, their nodal planes are also kind of rotating around with the SHmax orientation. And those are usually related to earthquakes happening below the sedimentary cover. So this is another indication of the consistency with depth. So, so it all makes sense. And what we can do with this is, if you know the state of stress and you know orientations of faults in an area, you can estimate how sensitive those faults are to an increase in fluid pressure due to, let's say, saltwater disposal. And I was part of a research group at Stanford that developed this tool, fault slip potential, that I know is pretty widely used. And what it does is it's a probabilistic tool that allows you to, it does a Monte Carlo process. So you can put in the uncertainty ranges as you know them for the parameters of interest, that's fault, strike, and dip, the stress information, the initial pore pressure. And so it's a simple program. It's meant to be a screening tool. The red lines here are the uniform distributions that it applies, and then the blue histograms represent the actual realizations of the Monte Carlo process for this particular fault segment. So you can do this for every fault segment, and it'll give you what's called the fault slip potential. So a value from 0 to 1, that is that the probability that in the uncertainty space that fault segment will end up on the wrong side of the more Coulomb failure line here. So again, it doesn't tell you for sure that we're going to have an earthquake or when, but it does tell you that fault is likely to be, critically stressed or not. So it's meant to be a screening tool that tells you how sensitive your faults are. And so in 2018, when we published the stress map for the Permian Basin, FSP was also new. So I did a demonstration of the FSP tool for the fault map that was available at the time, the Ewing map. The Texas Bureau is in the process of substantially updating that map right now, and I'll show some of that in a minute. And FSP, uses a uniform state of stress for each area, so we broke it up into domains because this is a complex stress field here, especially in the Delaware Basin. And on the right, you see those fault traces from the Ewing map, colored in traffic light colors based on their fault slip potential. So, red represents faults that have, that might be sensitive, and you might be careful injecting next to those. But also importantly, green represents faults that are probably so insensitive that you just wouldn't have to worry about them, and that's also useful. So, okay. Oh, and I'm going to talk about Permian Basin earthquakes, and an important point related to that is maybe the most important point here is you see the earthquakes. This is updated in 2020, and you'll notice they're not, for the most part, happening on known faults. They're almost exclusively happening on previously unknown faults, which is not, how anybody wants to do this. And so that gives you an indication of, the critical importance of understanding the faults. Okay, so in the Permian Basin, we are seeing a marked increase in seismicity. This is just magnitude 3+ earthquakes, just in this map area, just the ones I'm showing, starting in 1970. And so the catalog is probably, thought to be complete at magnitude 3+ since 1970. And you can see the seismicity kind of moves around the basin. These dots are colored by the time of occurrence, with the red being the most recent ones, and the size of the dot represents the magnitude of the earthquake. And so this is just largely to show that there's been a substantial increase in seismicity. And a number of studies have looked at this already, and they basically are in agreement that a lot of the modern seismicity, most of, but not all, of the modern seismicity is related to saltwater disposal, mostly deep saltwater disposal. But as you may know, the Permian Basin has a long history of earthquakes, some of which is natural. And also papers have been written since the 70s arguing that events going back at least into the 1960s may have been triggered by one industrial process or another, ranging from saltwater disposal to depletion associated with production, hydraulic fracturing, secondary recovery, a number of different things. And of course, on the west side of the Permian Basin is the Rio Grande Rift, and that's a tectonically active area. So, with higher strain rates. So we expect natural earthquakes here too. And this is a plot by one of my colleagues, Rob Skamal and Daniel Trugman, where they're showing going back to 2000, they're using what's called the Texar array, which is a network, a network here near Big Bend that was able to pick up Permian Basin earthquakes going, well back before the TexNet array went online in 2017. And, they're tracing the seismicity with these jagged lines here. Theirs is, they did template matching, so they were able to boost the catalog here. This was initially done by Chris Froelich and others at UT. And they're also showing oil gas production and millions of barrels of saltwater disposal. And so the saltwater disposal is the blue here, and you see that it starts to ramp up around 2010, and then it really ramps up rapidly after that. So now to look at the earthquakes themselves, because it's not a very simple story in some ways. It's not quite as simple as this looks. So we'll start in the Delaware Basin, and we see really quite striking patterns in the seismicity on the map. So this is the New Mexico, Texas border, so the southeast corner of New Mexico here, labeling the counties. The dots are earthquakes from Adam Begg and others from the abstract last year. And you see this very large amount of seismicity out here in Culberson County, what the Texas Bureau is calling the Culberson Mentone seismic zone. And very interestingly, there's this sort of horn of, I guess, of earthquakes coming off here to the northeast. You'll notice on this map to the right, showing a similar area that corresponds quite closely with this, what's called basement domain boundary, which is actually probably a very broadly distributed zone. It was, it represents that sort of fundamental building blocks of the crust, and probably there was an orogenic belt here, a broad zone, probably very faulted. And that, that was well before the Permian Basin existed, or even the Toboso Basin before that. This is like Paleo and Mesoproterozoic time frame, but it's just to say that the crust here has been through a lot, and there are zones of a lot of inherited structure. And speaking of that, the Grenville Deformation Front also cuts through here, also a broadly distributed zone in practice, and that'll be maybe more relevant when we look at the Midland Basin in a minute. But you'll note as we go down to the southeast into Reeves and Pecos counties, the seismicity starts to form these very, narrow lineaments that are well defined. And if you look to the right, they're following the SHmax orientation very closely as it rotates, and also going northeast as it rotates that way. So it's really quite a striking pattern. And note also on the right, these are TexNet locations. The events in the Culberson Mentone seismic area here to the northwest tend to be deeper. There's a wide range of depths represented, but they're a lot deeper than the ones here for the most part in the sort of southern part of the Delaware Basin. So we'll look at that in a minute. Also, the 2020 Mentone event, magnitude 5 here, if you notice in the recent Colson Draw event, which we'll look at here in a second, is right there. So I mentioned that this is not maybe the most as simple as the prior plot showed in terms of SWD increasing and earthquakes increasing, and this is partly what I mean by that. You could simplify the seismicity in the Delaware Basin and to some extent the Midland Basin into shallow earthquakes and deep earthquakes. And for the most part, as I mentioned, further north we have more of the deep earthquakes, and to the south in the Pecos-Reeves County area we have more of the shallow earthquakes. The shallow earthquakes tend to be smaller in magnitude, and so this is a cross-section here, interpretive cross-section by Peter Hennings and others for this area. It goes, here's AA prime, so it goes kind of across this northern Reeves County area. And this is to show that shallow saltwater disposal is predominantly happening into sort of two intervals, a shallow one and a deep one, and those happen to be where a lot of the seismicity, a lot of the seismicity is concentrated. So, Delaware Mountain Group being one of the areas, one of the intervals where SWD is happening in this area, particularly down here to the south. And there's also the deeper saltwater disposal into the Ellenberger Group and some of the slightly shallower intervals. This shows, might be hard to see, but there's a lot of fault traces on here from the new map by the Texas Bureau. This is Lillyhorn and others that they've shown. The orange lines here represent shallow faults that they've measured, and they're kind of represented here in the Delaware Mountain Group and Bone Spring Formation. These are strata-bound faults for the most part. They form these narrow graben structures. They're normal faults, and they appear to be, a little more steeply dipping than your average normal faults. And as I mentioned, smaller earthquakes, if you have smaller faults, you can't host especially large earthquakes. So, the smaller the fault, the smaller the maximum magnitude. And that may be what's happening here, where the deeper disposal, where it finds these basement rooted faults. So those are faults that, are in the basement, but might intercept the lower intervals. Where that pressure is able to percolate down, that might be where we get the larger earthquakes, because those faults in the basement can be larger. This is just to note, there's been over 30 billion barrels of saltwater disposed in the Permian Basin, with most of that just ramping up drastically in the last few years. Okay, so this is zooming in a little more on the Delaware Basin, and this is to show that there's a surface signature of some of the seismicity, or at least what appears to be the fault offsets for the shallower faults in the Delaware Mountain Group and Bone Spring Formation, and maybe a little bit in the salt above that. And so here's again the Mentone, the Culberson Mentone seismic zone. Here's the area we're talking about down here in sort of the southern part of the Delaware Basin. You see that rotation happening around here, and they've mapped faults partly, using 3D seismic and other approaches. And so you see the strikes of these faults also rotating around. And this is to show, there's an inset here. This is a an INSAR, so a satellite radar-based way of measuring ground deformation. So red represents up, and blue represents down over the 2015 to 2019 timeframe. So this is by Scott Stanowitz and others at UT. And you see, sorry, in this inset here, these lineaments that in some cases are that are formed by up and down surface deformation, and those are also parallel to those fault traces and to SHmax orientations, and in some cases to the lineaments of seismicity. But also note that there are faults mapped here, fault traces that are not associated with seismicity, but do appear to be associated with this surface deformation signal. And so the thinking is that these are faults slipping, even below the salt, but we're still seeing a signature of that up at the Earth's surface. And so this has been looked at by multiple research groups. This is Carissa Pepin and others at Stanford, and they also did INSAR work on this area. They modeled the fault slip using a dislocation model for a few places. I'm showing one here along the Reeves County line, and here they're showing 3 faults that they've identified in that fault traces they've identified in map view here. This is a narrow graben. And these are the 3 faults in cross-section view where they've done a dislocation model to try to match the surface offset to try to match the fault slip to the surface offset. And so, they've done a pretty good job. The red here is the surface deformation from INSAR. The black is the model results. And so even, accounting for the salt in between, they're able to see match that deformation pretty well. And what's especially interesting to me about this is that there's a lot, if you look at the amount of offset on these faults, which goes up in some places, they estimate, over 20 centimeters of offset over a few years, there's not nearly enough seismicity recorded at the surface to explain all that. And so the idea is that in this case, for example, they think about 98% of the offset is happening aseismically, and only 2% of that can be explained by the total moment release from the earthquakes that have been recorded here. So it's very interesting. It's probably because there's clay in these faults, or perhaps, and it might be because they're a little steeper than you might expect for dip-wise. But it's a good thing. There's less seismicity than there is deformation. Okay, moving further to the north, now looking at the deeper group of earthquakes. Again, this is where the bigger events have occurred. The November magnitude 5 happened here in this inset. This is work by Rob Skamal and others. It happened, as you probably know, quite close to the Mentone magnitude 5 from 2020. And so here I'm sort of showing where they are. Multiple studies have looked at this and come to the conclusion that probably the saltwater disposal wells nearby triggered that earthquake, and probably even triggered these far fields, these further, the concentration of earthquakes further to the west in the Mentone Culberson seismic zone. The blue are the disposal wells. In this area, most of them are actually shallow disposal wells, but there are, I think, 2 of them in the zone they've colored blue that are very high volume, deep disposal wells. And so, this is just a plot here over time showing the increase in SWD in this area, in the 30 by 30 kilometer zone around this, as well, compared to other 30 by 30 kilometer zones in the Delaware Basin. So it just shows an increase. And this is the red is a 30 by 30 zone in Oklahoma that was, that had the greatest amount of saltwater exposure. So these are very large volumes and rates. The work has not been done to attribute the magnitude 5.4 earthquake. I'm sure many people are working on that right now, but it happened in a kind of long bubbling cluster of earthquakes that were already kind of blamed on, SWD was kind of blamed for those earthquakes. So that would certainly be something people are looking at. And this is just to show the state of stress in this area. Delaware Basin has a complex stress field, and SHmax rotates, and this is sort of in the zone. So, this is the Mentone event, and this is the Colson Draw event from November. These events occurred in the area where there's some question about what exactly the SHmax orientation is. Is it east-west? Is it more northwest-southeast because it's rotating? It looks like both of the earthquakes occurred probably on slightly different in slightly different stress fields. This is more east-west planes, whereas one of the nodal planes in this beach ball is even closer to north-south and is also a oblique normal faulting event. But what is clear is that they happened on different fault systems and along this basement domain boundary, broadly speaking. So, okay, moving to the Midland Basin for a minute, we see something kind of interesting here in a slightly different way. This is looking at earthquakes just in the Gardendale area and just kind of around us, including the magnitude 5.2 that happened in December out here. We're looking at TexNet events with the white dots. The darker red ones are relocated events, so hypo-DD, but they only go through part of 2021. But you can see they form these, when they do the relocation, they form these very nice clear lineaments. And those are aligned along east-southeast striking planes, probably quite steeply dipping, and then a few kind of east-northeast striking planes as well. And the focal mechanisms, sort of support that too. But an interesting thing about this, I just got this figure this morning from Lily Horn, who is, she has done the interpretations and published fault interpretations over in the Delaware Basin, the Central Basin platform, and they have not published this yet. She's in the scissor group at TexNet, but they sent me this slide this morning. This is a preliminary view of their new map of faults in the Midland Basin for this area, and it is really, to me, it's quite striking. Well, first of all, so there's Odessa and there's Midland, and here are the earthquakes are maybe visible as dots in here, but at any rate, you can see they are happening on east-southeast and east-northeast striking faults that can be identified. In many cases, this is from seismic data as well as other sources, and it's apparently gone through a lot of QC work, and they've done a lot on it with contributions from the various sponsors in scissor. But you see these substantial faults here that are heading out to the east, kind of east-northeast strikes. Those are fairly similar to the SHmax orientation. So I would be very curious to see what their fault slip potential values are. But you see earthquakes heading off into the northeast like that, and this is near that Grenville deformation front. It kind of trends this way through this area. So, excuse me, the point, something that I think is really reassuring about this is that these faults can be mapped. They can be seen in the seismic, even though these are deep faults. These are what we're looking at here are basement rooted faults. And a lot of them are very steeply dipping, and so they've not had a whole lot of vertical offset, which makes them hard to see in seismic, but they can still be mapped anyway. And that's partly because larger faults can host larger earthquakes. So the faults you're worried about will sometimes be the larger ones. And so I think that's a very helpful thing, that when the due diligence is done and there's good seismic data and other sources of data, that we can actually see these faults. Okay, so to wrap up, I want to talk about kind of where we go from here, and part of that is acknowledging our limited capabilities in some ways, which I've alluded to a few times. And the Fort Worth Basin, I think, shows us a very nice example of both what we are able to do well and what our limitations are these days. So, as you probably know, there was an increase in seismicity in Oklahoma, or in the Dallas-Fort Worth area, shown by these gray circles, and then it's mostly declined, and that's mostly over now. But there were a number of felt events in the Dallas-Fort Worth area. At the time, the stress information was not well known there, but we mapped the state of stress, found SHmax is broadly north and southwest, quite consistent. More strike slip faulting to the north, mostly normal faulting further south. So we know the state of stress pretty well here. The same group at the scissor group, led by Peter Hennings at the Bureau, mapped the faults in this area as well. And so that's what we're seeing here. And since we know this is their new fault model for that area, and since we know the state of stress and the faults, we can do fault slip potential on them. You see a lot of red faults here, really a lot of red faults here, including quite a few that have not had any earthquakes on them. So we can compare, the fault slip potential values to to the earthquakes the faults that actually hosted earthquakes. And that's what we're seeing here. The top is the whole population faults as a function of their fault slip potential estimate. And the bottom are just the segments that hosted earthquakes. And no surprise is that the faults that hosted earthquakes tend to have higher fault slip potential values. They're more sensitive. But you'll note that the overall population has this very sensitive group here with fault slip potential values of 0.5 or more, which is quite a high value. That means more than half the time within the uncertainty space, these are critically stressed. And so what explains that probably is that most of these faults are in what's called area 4. So that's down here to the southwest, which experienced very little pore pressure increase. There was not much disposal happening there. So it's another factor that's important, the pore pressure. Because of that, the same group led by Rebecca Gao in the scissor group did a pore pressure model, a very detailed one that accounted both for production in the Barnett above, but also disposal at deeper intervals. This is a view of that. This is the maximum change, the maximum increase in pore pressure at any time between, let's see, the model goes from 2005 to 2018. So this is the maximum values, and the pink dots are earthquakes. They're labeled by the name of the sequence. The green lines are the faults that those earthquakes happened on. And you see there's, as I showed this one earlier, this is not a large pore pressure increase for the most part. 1 megapascal is about 145 psi. And actually, a lot of the earthquakes are happening in places where there just wasn't, there's not even that much pore pressure increase. And you'll note that there's quite a few faults here that have experienced a pore pressure increase and but have not had earthquakes, even though there's a lot of red faults on the map. So that kind of brings me to maybe a more pessimistic point, which is that there's related to the fact that we cannot predict earthquakes and may never be able to. And I think that's indicated here. I'm just looking at two of the sequences, the Azle-Reno ones again, and the Cleburne West earthquakes further south. And so here, these are plots over time of the pore pressure and fault slip potential. So pore pressure is the solid line, fault slip potential on the causative faults are the dashed lines here. And the dots are earthquakes as they occurred over time, with higher magnitudes on top. And so you see that this is the change in pore pressure, starts at 0, it kind of, starts to increase. There's no seismicity. Fault slip potential was not 0 in either of these cases. Of course, these are faults that are well oriented, about 0.18 in the Azle area and maybe 0.12 in the Cleburne West area, whatever those values mean. And pore pressure increases, consequently, fault slip potential increases, but it doesn't increase that much. Down here it goes from 0.12 to maybe, I don't know, 0.18 by the time the first earthquakes happen. And in the Azle area, it goes from maybe 0.18, and then the first earthquakes are at maybe 0.25. So, that I think we would all be hard pressed to identify, in advance when we were going to have a problem in these areas. I mean, more likely, you can just say these are potentially concerning faults. And in fact, the Cleburne case, you can see the pore pressure actually appears to have gone down, at least in the model, just before the seismicity occurred there. And then, it continues up in both cases, and there's seismicity that occurs here and there. In the Cleburne, it goes up quite a bit, and we only see more seismicity way out here, when pore pressures increase a lot. So I think, for one thing, this indicates that an importance of calibrating, the fault slip potential values in an area to what what you're seeing in some of the early seismicity. But it also indicates, I guess, a need to be humble about these techniques, because we can't say where an earthquake is, where a fault is in its earthquake cycle, right? It could have failed 100 years ago or 100,000 years ago and be ready to slip, and we are not able to do that yet, to know that yet. So on a more optimistic note, to close out, I want to point out that, and this is a fairly obvious point, that injection into areas where pore pressure has already been depleted due to production may be safer. So this is, again, looking at the Delaware Basin, the red are the earthquakes. This is work by Noam Dvory and Mark Zobak and the purple dots are Delaware Mountain Group oil and water production over time. So the depletion has happened mostly to the north. There's not a lot of seismicity to the north, and they're arguing that that's part of the reason. It makes perfect sense. This is just showing the stress path on the right, and we'll get into that. But what it means is that if you have control on the stress path, and you understand the pore pressure and parameters like the Biot coefficient, then you might be able to know where you are in terms of the stability of the critically stressed or best oriented faults in an area that's been depleted. So that's one way forward. I also mentioned that shallow areas, especially in the Delaware Basin, are hosting smaller earthquakes. However, detailed site characterization, monitoring, and due diligence are still essential, of course. Which brings me to my last slide here. I think this is a good example of a site that has done these things. This is a small carbon storage site, the Decatur, Illinois demonstration project. But what they've done here, because they are limited to being allowed very small earthquakes before they get shut down, they have mapped the faults in their area in 3D from seismic, and they know their state of stress in the area, and they have pretty good characterization of the stratigraphy. So they have already done good site characterization, but probably more importantly is that they're monitoring as they inject, and they've changed their injection plan according to what they see. So they were starting to see seismicity developing, microseismic events that no one would feel. So well before there was actually a problem at some of the greater depths. And so they plugged back and injected shallower to try to avoid that. And, time will tell. This is not very large volumes of CO2, but I think it's a good example. So thank you all. And hopefully this gives some ideas about where to go next and what is causing most of the earthquakes in this area. Thank you. Questions? Go ahead, Rebecca.
Early on in the talk, we were showing the three-dimensional modeling of the earthquakes and fault lines. Have you done an analysis that shows sort of a migration of the earthquakes along the fault over time, or
which area?
Change in magnitude of time? That was the one where you rotated it and showed it.
Oh, sure, in Oklahoma. Yeah.
And,
See if I can get back there.
Because it was really way back there. But
sure.
Has that kind of see if the magnitude is changing over time, or?
Some degree of that has been done. I think mostly with the prior catalogs in Oklahoma. People have looked at this. So what was the question? Like, are the magnitudes getting larger, smaller over time, kind of thing? I don't think that's if for a given fault population. I'd actually refer you to the paper on that by Park and others that just came out last year. I think they looked into that to some degree, and as I recall, they didn't find anything particularly, mind-blowing about the development of that could nail down which model of triggering of earthquakes. I think is what you're referring to. Is it like the whole patch, or is it a migrating outward from the center type situation? Yeah, as I recall, they haven't they haven't been able to constrain that, but we're gonna look a little more into that, I think, too. Yeah.
So on some of these big faults, I mean, are they being monitored where how it changes the pore pressure once that fault slips? I mean, are they monitoring the pore pressure to know, okay, that fault slipped, we don't have to worry about that fault for another 50 years? Or does it change the pore pressure in other faults as soon as it slips?
Yeah.
Allow the pathway to create pore pressure differences in other faults.
Well, about pore pressure monitoring, in Oklahoma, it's been done, but it's almost entirely not public. So, unfortunately, there's just not that much information about it. In the Permian Basin, you may have seen that the Railroad Commission is now requiring that in the seismic response areas, that downhole pressure monitoring needs to be reported every month on daily pressures every month. So that'll help with that. So, but I'm not aware of anything in the current currently known, partly because the data sets are not very complete. None. Yeah.
This is kind of Pat just asked, does that coefficient of friction, I mean, is it dynamic? Does it readjust after there's been a fault? When they go somewhere up or down or something?
Yeah, so I didn't get into rate and state friction, which is that this is, I was showing the coefficient of static friction, but when fault slip happens, depending on the nature of that material and the fault plane and the rate, that coefficient of friction can either increase, which makes the faults strengthen, less seismically potentially less likely to produce an earthquake, or it can weaken. And that depends partly on clay content. So a lot of the faults that are producing earthquakes, there's a dynamic weakening effect that happens and then it heals shortly afterward. Does that get your question? Yeah. And I didn't talk about, the clay-rich areas where, like in the Wolfcamp Formation, for example, where there's a high clay content, we actually see lower coefficients of friction there, as you may know, and those areas are also usually not prone to very many earthquakes. Yeah.
It looks like we're implying that perhaps in the Delta Basin, injecting the Delta Mountains to the deeper stuff because you're not going to be contacting with rare earthquakes. And if that's the case, is that also time pore volumes that are available in the Delta Mountains as opposed to say
that would contribute, it's a matter of how much pore space is available, but that pore space is already full of something, even when it's, there's been depletion, right? So you're either increasing pores that have already collapsed to some degree, and you're increasing them to the extent that they can be reinflated, or there's just not a lot of pore space to inject into in the tighter rocks. Does that? I don't think I got to your question very well there.
Well, you're addressing it.
Okay.
Yeah, I'm totally dark myself, but I know this Delaware Mountain is very, very thick, and we know it's got good porosity, but this kind of too much about it suggests it's got more injectability than Delaware because it doesn't have to do a lot of porosity.
Right. Yeah. So it's yeah.
But the problem is injecting the Delaware Mountain would cause problems with Avalon. Because they do that. Yeah. So there's a big consideration there.
Yeah, I don't think any of this should be taken to say that it's completely safe to inject anywhere, however you want to, right? The due diligence comment is important. But
that brings up an interesting point with the carbon capture. I mean, I think people see carbon capture as this huge nirvana of some solution to our problem, and yet people aren't talking about the potential faults and earthquakes and things that could cause.
Yeah, I think that industry is beginning to recognize that. Steve Metzger is here, and he can maybe say more if he wants to about that. But there has been over the years a sense that pore space is in some places basically empty, and you can just fill it with whatever you want to. But there's a pressure issue, and as we've shown, as I've shown earlier, the pressure is the issue here. So that's why depleted formations, or maybe shallower ones where you're not connected to big faults, or places where you understand your faults well, or offshore has been the Miocene reservoirs in the Gulf of Mexico are being considered heavily for this, also depleted. So yeah, I think that industry is beginning to understand that. Is that fair, Steve? Yeah. Okay. Anything else?
So if I understood your red and blue surface deformation map,
yeah. Try to go back to that.
There's only 2% of the deformation that's associated with a seismicity and changes in the depth there. So
what did that other 98% be related to?
So it's, I should say that they're talking about specific areas. So I'm not saying this is, 2%, 98% aseismic everywhere, but it is probably ductile, aseismic slip on faults that may have a higher clay content or something. And, there's patches, asperities that are failing, in a seismic fashion, excuse me, surrounded by, maybe, more ductily deforming rocks that probably are, in this case would be velocity strengthening in the rate and state friction context, if that makes sense.
So this is deformation without breakage. And is that right?
Yeah, I mean, you could think of it that, like, for example, if you're dealing with clays, this is a lot of it is micas moving past each other on their, flat planes, flat surfaces, without actual rupture happening, or stiff rock moving against stiff rock. I think this is seen a lot during stimulation too in the reservoir, clay-rich reservoirs.